All right, so today we are going to venture into combination circuits. Be honest with you, really the only way to do this is just to jump on in. So I've given you in your notes and what we see up on the board, the most simple combination circuit we can have. So what is a combination circuit? It's, as you'd imagine, okay, we're going to have resistors or things that provide resistance. They can be wired both in series and in parallel, all in the same circuit. And while this is an oversimplification of things, this is more representative of most of the devices and things that we use. We have all sorts of different branches on these circuits, handling different loads in different ways. So here's what we have for this problem. Okay? A nice simple 9-volt battery and 3 resistors. I don't think any of us are going to argue that the 5 and 7 ohm resistor are wired in parallel relative to each other, as they're on separate branches. But that parallel component of the 5 and 7 ohm resistor are wired in series to the other 5 ohm resistor. So everybody can kind of see how we're trying to describe some of this sort of stuff. Okay? Hopefully a nice, simple, basic combination circuit. You'll also notice on your notes, I have left you lots of space. Okay? The way in which we're going to solve these problems are going to be quite a bit different than all the other things that we've done before. Okay? I would like for you, up really high up at the top of this page, just to write yourself 2 notes. And you can write these kind of small because we are going to use most of the space for something else. Only in combination circuits, these 2 rules change. 1, okay, you can write this somewhere up at the top, preferably out to the side or whatever. Do not show your equation, substitution, and answer. Okay? We've trained you all year to go ahead and go through and make sure that you have the original equation, at least the rearranged equation, substitution, answer, appropriate units. You will not show that for combination circuits. The way in which you're going to show your work is entirely different. But I'm going to emphasize this here and make sure that is a point that is heard. It is only in combination circuits that these 2 rules are going to change. So later when we get to a test and you're just solving a simple series circuit, you're going to do what we've trained you to do for a simple series circuit, and the same for a parallel circuit. And when we get to combination circuits, we're going to do it a little bit differently. Item number 2 that is going to change. We're going to round everything to 2 decimal places. We're going to have a lot of little small calculations, and I do not want rounding error to be an impact on our overall problem. Okay, we still need to do it properly, but we're going to round everything to 2 decimal places in combination circuits. So those are going to be 2 things that are going to change. All right. So let's start off with step 1 in solving this problem. We are still going to, as we have done for series and parallel circuits, we're going to solve for each resistor's current, voltage, and power. Again, how we do it to look a little bit. Is this circuit done in proper schematic symbols? No. So if it is not, the first thing we're going to do is we are going to redraw the schematic. However, we are going to be listing information next to each resistor. So we need to leave a little bit of space. Here's what I suggest. You guys pretty much have a full page, blank page in front of you. In about the top third of that page, I would like you to redraw that schematic, leaving enough room next to each resistor. Okay, so for me, okay, I'm going to make it nice and large here. Okay, I would start with our battery. We will still label our 9-volt battery. Okay, coming around to 5 ohm resistor here, 7 ohm here, and yours could look a little different than that. That's okay. 5 ohm resistor there, and then back around to the negative terminal. We still will label our resistances, 5 ohms, 7 ohms, 5 ohms. We will not draw the conventional current flow onto it. Okay, we just leave it as it is. Okay, but we have those 3 resistors. And actually, I'm just going to change this just a little bit, just because it doesn't really matter the way that's drawn, but make it look a little bit better. There we go. Okay, so that's what we have in terms of our standard schematic symbols. Now the first thing we're going to do once we have that is we need to go through potentially a series of steps. And we're going to break this down based on its equivalent resistance. So, here's what I'd like for everybody to do. Only using your calculators and not writing it down, I want us to find the equivalent resistance between the 5 ohm resistor and 7 ohm resistor that are in parallel relative to each other. So, inverse of 5 plus inverse of 7, inverse of whole quantity. And since I no longer have a calculator, I need to rely on you to give me a little bit of help with this. 2.92. And thank you for rounding that to 2 decimal places. Everybody agree with 2.92? Good. So remember, what does that 2.92 mean? It means that if we were to take these two resistors out and in its place put in a 2.92 ohm resistor, the circuit would behave as a similar circuit. So now in the middle third of the page, we are going to redraw this circuit. Now this is not an actual circuit, but it is our way of kind of understanding the mathematical equivalent of it. So again, in the middle third of the page, we will still have our 9-volt battery, but now in place of what was the 5 and 7 ohm resistor that were in parallel to each other, now we're going to put the 2.92 ohm resistance there. Did we touch the 5 ohm resistor that was outside of that? No. So we will still draw that in its place, and then we will come back around. So that would be a 5 ohm resistance there. So again, this would be an equivalent circuit. Not a real circuit in comparison to our original, but mathematically equivalent. And our goal with breaking this down is we need to get to one battery and one resistor. So are we there yet? Nope. Okay. So we'll have another step to do. Okay. Now we have the 2.92 ohm resistance and the 5 ohm resistance. How are they wired relative to each other? They're in series. Hopefully we don't need our calculators then. What's the equivalent resistance going to be between those two? 7.92. So now in the bottom third of your page, okay, we have a 9-volt battery, okay, going around. And I have the tendency when we get to this last one to stick it off to the side just because it's easier to list things, which is what we're about to do. So 7.92 ohms. So what does this circuit that's drawn here at the bottom, the schematic there mean? It means that in the entire circuit, the equivalent resistance is 7.92 ohms. Now, depending on the problem, we would have a different number of steps to get from where we start to one battery and one resistor. This one was pretty simple and it took us 3 steps. Okay? You might have some more complex ones that you can also potentially do in 3 steps, but it just depends on the schematic that we have. And the more complex it is, usually it might take a couple more steps for us to get there. Okay, so that's step 1. Okay? We take this using only the equivalent resistance equations. We're going to break it down all the way until we get down to one battery and one resistor. Then we're going to start with this 7.92 ohms, and we're going to work our way slowly back up to our original schematic. And we do this by asking ourselves 2 questions. The first question is, in this last circuit that's here, the 9-volt and 7.92 ohms, in terms of Ohm's law, what's missing? So what is Ohm's law? V equals IR, so voltage, current, resistance. Okay, so what's missing? Okay, we're missing the current. So we need to solve for the current in that schematic. Please, using only your calculator, since we're not writing down equations, go ahead and solve for that. V equals I times R. Hopefully we can do the algebra to rearrange that. Alicia, what do we get? Hopefully. Okay? Do we all agree with 1.14 amps as our current for this? Okay? I'm going to color code this a little bit because it's easier for me to do on the board while we do that, just so we can kind of understand the steps as to what we're doing. So this next step is going to be in red. Not that red indicates anything, but we had 1.14 amps. So that was the first question that we asked ourselves of 2. The next thing is, now that we have everything in Ohm's law for the resistor that we have here in this set, we're going to slowly work our way back up to the next schematic. And please pay attention carefully to the question that's about to come. As we go from this resistor to these 2 resistors, how are these 2 resistors wired relative to each other? They're in series. Now the reason why that question is important, because the answer to that question determines what information we pull from the previous schematic. And in a simple series circuit, what is the one thing that remains the same across all resistances? The current. Okay? So that means that since they are in series with each other, this current gets carried up and applied to both of these resistors. So this gets 1.14 amps, and this gets 1.14 amps. Now, if those resistors were in parallel related to each other, what do you think would get carried up? It would be the voltage, okay? Because in simple parallel circuits, it is the voltage that remains constant across those devices. Okay, now we're going to work with this middle schematic. Let's go to green, okay, in our next step. Now we have these 2 resistors. We go back to question number 1 again, which is, in terms of Ohm's law, what's missing? Now we have the individual voltage drops that are missing for those. Okay? Take a minute, calculate both of them. Catherine, what do we get for the 2.92 ohm resistance? Okay, units? 3.33 volts, good. And then we have our 5 ohm resistor. Rissa, what do we get for the 5 ohm resistor? Okay, 5.70 volts. Do we as a class agree with that? Okay. Now I understand there's a little bit of rounding error with that. I know some of you might want to try to go ahead and say, all right, try to add that up. Don't worry about that, okay? That's okay with where we are right now. Now, here's the deal though. If we were to go back to our original schematic, this 5 ohm resistor, did anything really change between, this resistor here on the right-hand side versus this 5 ohm resistor here? No. When nothing changes, everything gets carried up. Okay, so we can go ahead to, we have the 1.14 amps. Technically that was from the previous step, so 1.14 amps. Then we also had the 5.70 volts. But we have to deal with this 5 and 7 ohm resistor that are in parallel related to each other. So, do it again. As we go, the question is, as we go from the 2.92 ohm resistor to the 5 and 7. How are the 5 and 7 wired related to each other? They're in parallel. So what gets carried up? The voltage. So now we get 3.33 volts here, 3.33 volts there. And one final time, in terms of Ohm's law, what's now missing for the 5 and 7 ohm resistor? The current. Let's go ahead and find that, please. Anuj, what do we get for the 5 ohm resistor up top? 0.67. We get 0.67 amps. And also for the 7 ohm resistor, 0.48 amps. Okay, one last step, and we can only do this once we get back to the original schematic. We need to find the power at each resistor. Okay? There is no point in doing it in any of the previous schematics. We have to wait until we get all of the available information for the resistors that we have there. So now we have 3 resistors. We should be able to find 3 powers. So voltage times current should be a pretty easy thing for us to do. Done it already? Okay. All right, Aaron, why don't you help us out? The 5 ohm resistor that's up top, what do we have for the power for that? 2.23 watts. How about for the 7 ohm resistor down below? 1.60 watts. And then our final 5 ohm? 6.50 watts. Do we all agree with those values? Okay, awesome. Now, just kind of a friendly reminder about the process as a whole. One, if we don't have a proper schematic, we do have to redraw that. It's not going to be for a lot of the cases, but for the 2 sample problems we're going to be doing today, that's what we have. But I think now we can see, especially for this original schematic, we have to list 4 things next to each resistor. So when we draw these, please leave enough space for that. You need to be able to read whatever's there. Okay? So our first real step is going to be to break down these circuits using the equivalent resistance equations. We have to get down to what? 1 battery and 1 resistor. Okay? However many steps that's going to take. And you know what? Let's say for a little bit more complex problem, let's say Nick and I are working on the same problem. Nick may do it a little bit differently than I do it, and that's okay, as long as we're following the same process and we're using the correct equivalent resistance equations. Okay, so as long as we break it down, okay, we get all the way to that point. Okay, so once we then break it all the way down to the single resistor and the single battery, then we start to work our way back up. What's the first question we ask ourselves? What's missing from Ohm's law? Okay, so we will have the battery voltage in this schematic. That's the only place we really use the battery voltage after that was done. And obviously we're going to have the resistance at that step, so we solve for current. Then, as we start to carry up, the question that we should ask ourselves is, as you go from that resistor to what's up at the next level, how are those resistors wired relative to each other? If they are in series, what gets carried up? The current. And if they're in parallel, what gets carried up? Voltage. Okay? And then we'll just keep climbing that ladder until we get all the way back to our original schematic. And then, and only then, will we solve for the power of each resistor. One final thing before we move on to the next sample problem. I'm going to phrase all of this as they're all resistors that are wired into these circuits. But I would like for you to understand that no matter what it is, let's say it is an electric motor that we have in there, in the circuit, and not a resistor. That electric motor has its own, what we call internal resistance. It's going to provide resistance when we use it. So even though it's just a resistor, and you just may see it as a field of resistors, these apply to most circuit components that they're going to be applying resistance as we start to deal with things. So we are modeling a lot of what we will see in some of our circuitry components. All right. So what I want to do is I want to kind of halfway get you started with this problem and then have us finish. Okay, so this is on the next page of our notes. Okay, so first things first, let's go ahead, let's draw the schematic just at this step. And I would also say in about the top third of the page, okay, redraw that schematic to leave enough space. The conventional current flow you do not have to label on this. We're fine with you not labeling. Okay, so as we're drawing this, okay, I'm starting to throw a little bit of a monkey wrench into this because I want to get you to think about things a little bit differently. And again, they're going to start to be a little bit more complex depending on what we're going to see. This is not a trick question and one I genuinely would like you to think about before you answer. Take a look at the 8 and 10 ohm resistors. How are those wired relative to each other? They are in series related to each other, and I hope we can see that. Okay? How are the 2 and 6 ohm resistors wired relative to each other? They're also in series. Okay? Now, the first thing is going to be that we're going to have to deal with, and I'm going to suggest, deal with the most complex parts first. When you have multiple things going on in the branch of a circuit, it's going to take, and it must take, multiple steps to break it down. You cannot, even though I know you can probably do it in your head, it's wrong for many reasons. You cannot go the 2 and 6, 10 and 8 all together down to one resistor in one step. We have to separate that out. So we need to do the 8 and 10 ohm resistor in series, solve for that. The 6 and the 2 ohm resistor, solve for that, before we can go to the next step. And again, I know with these numbers especially, you think, oh, it would be pretty easy, Calvo. I can just go ahead and do, okay. You'll see why when we start to work our way back up, that doesn't work. Okay, so let's go to our next schematic, somewhere about the middle third of the page. Okay, we still have our 24-volt battery, one resistor up top, but we can break that down now to one resistor on the left-hand side of that branch and one on the right. Okay, so 12 ohms up top. That doesn't change. The resistor on the right, what does it become? I don't think any of us need to use calculators for this. Should be 18 ohms on the right-hand side. The left-hand side of that needs to be 8. Okay, you tell me, what's the next thing we're going to do in breaking it down? Okay, what's going to get turned into series? You chuck it all in together? The 8 and the 18 are wired in parallel, so we do need to calculate this one. Okay, let's find the equivalent resistance for the 8 and 18. We're not quite going to get all the way down to one battery and one resistor. But 24 volts, that 12 ohm is still going to stay. We'll break that down to another singleton. Kendall, just curious, did you happen to get that value? 5.54. Okay, 5.54 ohms for that. And we all should agree that's what we should get. Okay, which should make this last step nice and easy. Okay, we have to go to one final schematic. Okay, 24 volts to our singleton resistor. Now that one would be 17.54 ohms. Now, any questions on our breakdown process with this one? Okay, so here's what I would like for you to do. Okay? I've helped you to get to this point. I would like for you to start working your way back up through this. And as you are doing that, just keep in mind the two questions that you're going to be asking yourself. Okay? Go for it. Now you're going to finish the problem. Carrying it back up. Okay, figuring out what carries up, what do we still need to solve for, and go from there. As you do that, I'm slowly going to put answers up on the board so you can just start to check yourself as to where we are with different parts. Friendly reminder, how many places are we rounding to?
Is there a particular reason for that, or?
There is a particular reason for it. Especially when we get to ones that are even a little bit more complex than these. I don't want you to get lost in details of carrying that one more decimal place, having that value be enough, and then any rounding error that we have. And Nick, truth be told, we could make a rounding mistake at any point. It's not like that's going to help us with that, but it's just I think it's going to help us a little bit more and kind of keep track of it and keep track of our numbers properly. Is this like a standard rule for electrical engineering? Not really. It's just for our intents and purposes, just keeping it a little bit more manageable. Okay, hopefully most of us are getting what we see. Okay, so the 12 ohm resistor up top getting the 22.52 watts. 2 ohm resistor on the inside, 1.81. 6 ohm resistor, 5.42. Then on the outside of the last two, 1.76 for the 10 ohm, and then 1.41 watts for the 8 ohm resistor. Seems to be doing all right with it? No. Okay? So then let's take a look at what do we have concerns about. And let's actually rewind to this slide, because this slide is actually probably going to help us to identify more of our concerns. Why doesn't the volts get carried up to the last one? What do you mean?
Because they're all in the same parallel circuit, so they not have the same voltage as the one, like as the 8 and the 18.
What about them?
I'm just confused how.
Okay, remember, where do we go as we're working our way back up? It's a good question. Okay, as we go from the 5.54 to the 8 and the 18, how are the 8 and the 18 wired relative to each other? They're in parallel. Okay? So from the 5.54 ohm value, we carry that voltage value to the two of them. Okay? And then again, we'll solve for what's missing. So that's why at this step, they both have the 7.59 volts.
Yeah, but then when we come up here.
Correct. Okay? Then, keep in mind, as you go from what to what, let's start with the 18 ohm resistor. Yes, it's in a parallel branch, but be careful. How are, and that's kind of why we have to be careful about the way we word it, how are the 8 and 10 wired relative to each other? They're in series. So the current from the 18 is what gets carried up to the 10 and the 8. And likewise, even though it's on a separate branch, from the 8 ohm resistor, we carry up the current from the 8 ohm resistor to the 6 and 2. And my guess is for a lot of us, that's kind of where our hang-up might have been. Okay? Now, one more thing to kind of add to it, and I kind of said it in the front side of this problem, but that is the reason why we can't go from these 4 resistors straight down to a singleton. Now you can calculate pretty easily that that was going to be 5.54 ohms, but when we start carrying things back up, we're not going to carry the right things up as we start to work our way. So that's why anytime you have like the series within parallel, and we haven't seen it yet, but a parallel within a parallel, we have to solve for that in their own individual steps. We can't just do a clean sweep on everything and try to bring it all down to one, because it will impact us when we get to the end. Okay? All else good?